Right. Well, we were talking about cyclic group last time, classifying, and what we have up to this point is it's really kind of a neat little package that's tied up in. A cyclic group is either infinite, in which case it's isomorphic to the ordinary integers, or it's finite, in which case it's isomorphic to z mod nz, where n is the number of elements of the group. We're going to use these ideas to talk about orders of elements. So here's the first theorem today. Let G be a group and let X be some element of G. And suppose X is n, where I'm going to allow n to be infinity as well. So there's two things that can happen. Number one, if n is infinite, so if the order of X is infinite, then the order of any power of X other than zero is also infinite. And if n is finite, then the order of X to the a power is whatever the order of n it's n divided by the GCD of whatever a n is. So let's see what's true. One, suppose right, you order of X to the a, well, let me put it this way. If the order of X to the a is finite, then if the order of X to the a is finite, then there exists k in the natural numbers such that X the a k is 1. Right? So there's some positive power of X to the a to get you 1 if the order of X to the a is finite. This implies but since the order of X is infinite, this implies that AK must be 0. Right? Because there's no non-zero power of X that's going to give you the identity. And as K is in the natural numbers, that is, K is not 0, so that takes care of it. That. The more interesting thing is what happens in finite case. For 2, let's suppose, well, first note, notice that X to the a notice n divided by the greatest common divisor of a and n is an integer, right? So this makes sense. This is an integer. X to the a to whatever the integer power. This is X to the n. So notice I've just swapped out the a and the n here. Now, this thing is also an integer because the GCD of a and n, well, it must divide a. So this is an integer. And this is 1 because this bit is 1. So what does that tell me? The order of X to a must divide because I know that X to the a to this power is 1. I know that the order of X to the a must divide this power. I haven't proved that, but you will because it's in the homework. That's one of the problems we have there. Now suppose right, so I know that the order of X to a must divide that. I want to prove that it's exactly that. So let's suppose that x to the a to the d power is equal to the identity. So AD is a multiple of n the order of x. And so I'm going to write that as, I'm going to write this out kind of explicitly. Right. AD is a multiple, right? So that's, I've kind of captured that there. Now, I'm going to write A now let me ask you a question. What is the relationship well, so let me write this out. So in K, instead of A, I'm going to write my dramatic A prime times GCD N times D. What can I say about the relationship between A prime and N? He's right. Everybody agree with that? A prime and N must be co-prime. Right? They can't have any factors in common because I pulled all the common factors out of this, right? Since GCD of A prime and N equals 1, then notice A prime divides this. So what do I conclude? A prime divides this product here, but A prime is co-prime to N, then what must be true? Okay. So I will write K is K prime, A prime. So now I have N K prime, well, cancel the A primes. And I do cancel the A primes, and I get NK prime is equal to GCD A, you know, by okay with it? So let me rearrange this. Right. Now keep in mind, this ugly looking color right here is an integer. And notice now divides. So we know that the order of x to a must divide this, and also this thing divides any power of x to the a that's 1. So n over GCD a n is equal to the order of x to the a. And that's any questions? I hope this also sort of starts to illustrate to you why problem number 1 had to do with properties of the integers, because these come up in these kind of things all the time. Here's a couple of here's a theorem about, cyclic groups and their subgroups. Before we get into the proof of this, I'll give you a couple examples. They're kind of interesting. Theorem. Right. Suppose G is a cyclic group generated by the element X. Right. Number one, if the order of X, if this is if the order of X is infinite, then anybody want to take a guess? So what I'm doing is I'm saying, okay, look, my X generates infinite group. See, when does X to the 8th power also generate all of the group? For the finite case, it's a little bit more exotic. Yeah, order of X, yeah. No, it's this. Then X yay is equal to G. If and only if. Anybody want to take a stab at this one?
Is it for cocaine and or cocaine?
In this case, the number of generators of G is Pn. Remember what this is. This is the Euler phi function. This counts the numbers between 1 and n that are relatively prime to n. Let me give you an example. I'm going to write these additively, even though this theorem is written multiplicatively. There's an infinite cyclic group. It's generated added by Z. 1 plus 1 plus 1 forever, and then all the negatives. Agreed? Give me a number. Not 0. 5. Okay. What is the subgroup generated by X to the 5 here? So the analog here is when generator X is 1, but now I'm additively. So instead of 1 to the 5, I really need 1 plus 1 plus 1 5 times. Well, let's see. Better have 0, 5, 10, 15, 20. I agree. Give me any other number. 7. Well, the subgroups look like the freaking multiplication tables from grade school. That's essentially what it is, right? It's just all the multiples of that. Notice, this is kind of weird. Would everybody agree that this is a proper subgroup? There's stuff from Z that's missing here, right? This is a proper subgroup. But they are isomorphic. Because they're both cyclic. What's the generator of this? 5. Generator of this is 1. Here's the way the isomorphism works. Just take everything you multiply by 5. This is, you can check this is a homomorphism from Z into 5Z. Multiplication by 5. It's 1 to 1 and on to, right? And it preserves the group structure. So this is interesting because this group has got a proper subgroup and it's isomorphic. In fact, every proper subgroup of Z is isomorphic to Z, with the exception of the identity. That's perfect. So, the infinite case, yes,
You said it looks like it's a proper subgroup. It is a proper subgroup, right? Or
it is a proper
okay, I just
subgroup,
want to make sure.
but it looks like the original group because they're isomorphic. Let me give you a finite example. Now let's see what happens here. What are the subgroups of this? Actually, in this case, I can list them all. Okay, so there's the two silly ones, the identity and the whole thing. This is a subgroup generated by two, the analog of there is x squared. This is subgroup generated by three. It's got four elements. Subgroup generated by four. It's got three elements. And there's a subgroup by six. That's two. Right. I noticed I went through generators. This was generated by one, then two, and then generated by three, four. Why did I skip the subgroup generated by five?
That might just take some thought.
That is correct. This is part of this Euler fee thing. So. Two times two. Notice there are exactly four elements in Z12 that don't appear in any of the proper subgroups, right? And those are 1, 5, 7, and 11. Those only appear in the full Z12, right? They don't appear in any of these others. And what do those four things have in common? They're relatively prime 12. Well, yes,
Like you said, the identity is the only subgroup where it's not as important to Z. But is the identity like 0 or 1? Or depend? Okay.
0, because over here our operation is addition.
Okay, and then multiplication is 1.
Yeah, we're good. So this theorem is written in a multiplicative fashion, right? But for me to do this multiplicatively, what I would have to do is do like the powers of x, or I would say x to 1, x to 2, x to 2. I just want to correct that. Yes, sir.
I can verify what would 8 be, 9 be, and 10 be in terms of those subgroups down there if they were generated?
Oh, right. What would 8 be?
Yeah.
Okay, that's a great question. Gotta be one of these two, doesn't it? Right?
Yeah.
It's gotta be one of these two. So which one is it? Well, it's gotta be the smallest subgroup containing A, right? So if it's generated by A, what do you got? Well, once you got 8, then you've got 8 plus 8, which is 16. Oops, too big, so that's 4. And now you've got 8 plus 4, which is 0. So it's sort of the most economical one. Yeah.
Why, you said the least one that contains 8, what's motivating your thought there? Why would be the least one that's containing 8? Why not?
Well, notice that this one sits inside of this one, right? Agree?
Okay.
So if what you're gonna do is say, okay, I wanna see what the group generated by 8 is, it's gotta be the small, right? There's no way you're gonna make these extraneous things A,
Okay.
right? So you're just making small singles for it. Another, I'm glad you bring this up, we're gonna characterize this later, but if you look at the subgroup generated by any element, it is the intersection of all subgroups containing the element, right? And so for A, you've actually got two of them.
I have one more tangential question, sorry. If I did like 7Z and 5Z, would those be isomorphic?
Yes.
Okay.
Yeah, because they're both isomorphic to Z and it's transport.
Oh, right, got
And
it.
so to get from 17 to 5Z, it would be kind of stupid because you multiply everything by 5 sevens, but it works.
Okay,
Okay, right. So let's proof this one. Well, the claim here is XA is equal to G if and only if A is plus or minus 1. Right, because we're assuming that G is generated by X, so that's pretty straightforward. On the other hand, for the other direction, let's suppose I'm gonna do the composite of this question. Let's assume the absolute value of A is bigger than 1. So A is not plus or minus 1 or 0, right? And what we want to do is show that X to the A can't be. So if because after all, G contains X. And so if X to the A, if powers of this make all of G, then that means that a power of this must be X. So there exists D in the natural numbers. Such that you can X to the actually, let me just this instead of that, I think it's kind of muddy waters. Let's just say the non-zero limit. Such that X is the A, D, it's X to the 1. But as absolute value of A, 1, it's not. So the first result, I don't think is too surprising. And of course, the second one is kind of more intriguing. Now let's suppose that X, the order of X is n. So that means that G is generated by this element of order n. It means that G is cyclic of order n, so it's G is isomorphic to Cn. So let's suppose first that X to the A is equal to H, or G. Of course, just like I pointed out in the proof before, this means that X must be in X to the A. AD equal to 1 mod n. Finding the exponents. And this equation, well, let me see, it's congruous. So. If and only if greatest common divisor of 1. So it's congruence, then A and N have to be relative. And on the other hand, if this congruence is solvable, or that is, and yeah, GCD equal 1, then what do we know? What about beat into your heads? There's C and Z. Such that C A is equivalent to 1 mod n. And so, in this case, X to the A C power is equal to X, well, X to the 1 plus some power of n, but that's equal to 1 mod n. So what does this mean? This means X, which is the letter you need to generate all G, is in there. Therefore, all of P derivates. So we got it to work in both directions. Okay. Any questions on that? Yes, ma'am.
If A is -1, is that like the inverse, like some shoes to the inverse?
Right. Because remember, when you generate a group of words or letters, then you're allowed every letter or its inverse. Okay. Let G be a cyclic group generated by X. Number 1, and this is a big, any subgroup of G. So this is a big deal. If you have a cyclic group, any subgroup is also cyclic. So if you generate a group just by one letter, then any subgroup can also be generated by a single letter. This is actually, and again, this depends on properties, the integers and the C's. If you replace any city, yes.
Does this have to do with what we were talking about earlier, since the cyclic group is isomorphic to the integers?
Yeah, any cyclic group is isomorphic to the integers or the integers mod n.
Right.
Yes, but don't know at this point that any subgroup of, so if you have like say 100,000, how do you know there's not a subgroup in there that requires two of the powers of X to generate? Right, and that's what we're gonna sort out. Yeah, the order of G is equal to n finite, then for each K and N, it's just that K divides N, there exists a unique subgroup of G, of order K. We saw this in this last example, because remember how I put like, C12 up there? What are the divisors of 12? 1, 12, 2, 6, 3, 4, right? We had one and only one subgroup that we found each of those divisors. This is also wildly untrue for general, right? The group on the Rubik's Cube. There are divisors of that group, that there's no subgroup of that order. Okay, proof. Yes,
It's unique, isomorphic.
yes. Well, no, it's unique, period. If you get cyclic subgroup, right?
Oh, sure.
Because, for example, in S3, there is a subgroup there's a subgroup for every divisor of 6. There's 3 subgroups of order 2, right? They're all isomorphic, but, no, I truly do mean unique here. But H, indeed, be a subgroup. And I'm gonna say H is not, the identity. So a non-trivial subgroup. I want to look at this. Let A be the set of K in the natural numbers such that, X to K is in K. And recall, X is the generator. Okay, so I'm gonna look at the set of everything in the natural numbers such that a power of X is in H. This set is not empty because H is a subset of G, so everything in H is a power of X, right? Because everything in G is a power of X, so everything in H is. If this is a non-identity group, then there has to be some positive K's. You might say, well, Jim, what if it's only negatives, right? What if only negative integers, X to K is in there? But that's okay, because if X to the minus 12 is in H, then X to the plus 12 is in H, because that's the integer. Everybody okay with this? This is not empty because H is a non-identity group. It's not just one. So what do you know about this set? What is the least thing you know about this set? No, it doesn't contain 0 because it's a subset of the natural numbers. Well, what do you know about any non-empty subset of natural numbers? No, that's it. It's got small stuff. But I claim this is going to be my generator. Thanks. Yeah. Let me prove this. Notice X to the 8 is an element of H by definition. Because A is power of X that's in H. So the subgroup generated by X to the 8 is contained in A. Question: how do I know that's everything? this containment was easy. I need to show that every element of H has actually contained it here. Any ideas? Yes, yes. Yeah. H equals X. Okay. Some. Okay. I'll assume the natural numbers just to make it easy, it doesn't really matter, because if this were a negative, all I do is take the inverse of it and it would be a positive, right? Right, K is equal to Q A plus R. Okay, right, with now notice that X to the R is X to the K minus QA, right? This is X to the K, which is in H. X to A is also in H, so this is in H. Right? Since X to the R is in H, and R is less than A, what follows from this? R must be zero. Because A is minimum. So we have that again, putting out, doing something things. Okay. Any questions? I do want to address this statement here. This is an important one. If you have a cyclic group of order n, then there is a subgroup, a unique subgroup, everything dividing it. Let's suppose in part two, G is generated by X, and the order of X is n. What we want to do is let's suppose that A divides n. I need to find a subgroup of this order, and that task is fairly easy. I'm going to let H. This is the set of elements X and G such that X to the A is one. Notice I'm not saying that the order of X is one. I'm saying actually the order of X divides A. I'm sorry, I'm not saying the order of X is A, I'm saying the order of X divides A. So for example, the identity is in the set, because if you take the identity to the 8th power, you get 1. So notice that and A is an element. This is a subgroup. It's easy to verify this, and it must be generated by an element of order A. And this element up here is an example of an element that has, order A. So. A has exactly a. So at this junction right here, I've got sort of what I stated. What I have so far is if A divides N, okay, I found the subgroup of order A. Big question. And in fact, that thing right there will generate a subgroup of order A. It's the only one. That's the big question. Why can't there be multiple subgroups of order A? We've seen this happen in other groups, like, for example, S3. So for uniqueness, K is another subgroup IG of order A. So note K is cyclic. Let X to the K be K. Because we've already shown that any subgroup of a cyclic group is cyclic. So K is a subgroup of G is going to be cyclic. And it's going to be generated by something. And by something, I'm going to call it X and K, because I know that its generator is an element of G, so it has to be a power effect. So I'm going to say this. And note that the order of X to the K is equal to A. Because I'm assuming that this generates a subgroup of order A, so its order has to be exactly A. It goes exactly through A things to make the elements of the group. Since H is the set of C and G, such that C to the A is equal to 1, X to the K is in H. Because X to the K has order A. Therefore, K is a subset of H. And this really finishes it for me because here's what I know. I know that because the generator of K is in H, then K must be a subset of H. And I also know that the order of K and the order of A are both A. So if I've got a subset of 12 things, and that subset has 12 things in it, they must be the same. And so there's the uniqueness. Okay, any questions? Okay, I'm gonna finish out this business where we're talking about groups that are generators. Let me give you a couple results that come with it. Proposition 329. This is also an important result, and actually, your question earlier. Well, actually, both of your questions earlier. This is kind of a good place for them right here. If G is a group, any group you like, no longer necessarily cyclic, and HI, I in some index set is a family of subgroups of H. I'm sorry, subgroup of G. So I've got this collection of subgroups of G. Then the intersection of all them So. I mean, quick proof of this. So this is a big result here. Because it says, if I have any collection of subgroups in the group and I intersect them, that's a subgroup. Okay, I'm gonna use the subgroup criteria. First question, this intersection right here, can it be empty? How about? Right, every one of these subgroups, so they all contain the identity, so this is a non-empty set. So glory be me, I can use the subgroup criteria, right? Not empty as the identity of G. So. So this means for all I and I, X and Y are in each other. Right? Therefore, for all I and I, X, Y inverse is an HI. Right, because each one of those HIs are groups, and so if it contains X, Y, it just contains X and Y inverse. And therefore, X, Y inverse is in every one. And there you go. Subgroup criteria gives us that this is a sub. Okay. Just a couple more things. Here. Um, let's keep the group. And a subset of G. And I do mean a subset here, not necessarily group. The group generated by A is given by this is the fancy math way to do it. And then after this, I'll show you the workaday way to do it. This means the subgroup generated by the set. This is the intersection of all subgroups H and G, such that A is contained in H. So when I say the group generated by a set, this is the intersection of every subgroup of G that contains that set. And we saw that in that question you were asking about Z12. You asked what's generated by A. It's the intersection of all the subgroups that contain A. And there you go. So let me ask you this. What happens if A is the empty set? What is the group generated by the empty set? How many sets contain the empty set? All of them, right? Every set contains the empty set. So every subgroup will contain the empty set. What is the intersection of all subgroups of G? Can you identify it? It is the identity, correct? Right. If A is all of G, then that intersection would be G. From a practical point of view, so here's the working person version, and you can look at the notes of this. You can make, this is exactly the same as the words I told you before. the group generated by A. It's just all words you can make of the letters of A, right? This is what we discussed before. These two definitions coincide, or well, they're equivalent. You might see if you can figure out why these two. Okay, any questions? Questions? All right, well, I will see you folks on Friday.